So today on nonlinear constitutive behaviors writ large in the context of finite element methods, we're going to cover a few different, major questions. First, we'll kind of answer this question of how exactly do we include nonlinear behavior in the context of a finite element method, and how exactly does that kind of affect the way that we've set up our solution procedures in this finite element context. We'll then define what exactly I mean by a material model and how does that reasonably approximate the behavior of materials that might exhibit some nonlinear relationship between stress and strain. I'll give you some particular examples of what these material models might look like and what different behaviors or constitutive behaviors they're intended to represent, when you might use them, what types of materials they're used for, things like that. And then finally, I'll show you exactly how some of these models are constructed in a relatively simplified one-dimensional sense or viewpoint. And that'll kind of give you a nice intuitive understanding of exactly how do these different models behave and how they generalize in the case of, looking at things in a much more complicated sense and developing these fully three-dimensional constitutive models relating, all the different independent components of stress and strain in a 3D setting. Honestly, constructing material models from that starting point would be a little bit hard to swallow. So I find it's a little bit easier to start from the one-dimensional perspective. All right, so first of all, we talked in the past, last week rather, about nonlinear analysis. We said nonlinear analysis in general introduced this nonlinear relationship between the internal forces that result in some structure and the corresponding displacements at the nodes of that structure. But I want to point out that especially when we're considering problems that involve nonlinear behavior, where the relationship is no longer linear between forces and displacements, it can happen either in the case of geometric nonlinearities or material nonlinearities. In general, in either one of those cases, the typical approach to solving these problems is not to simply say, well, let's take our structure and take whatever loading we're going to put on this structure and then just apply it in one single step, basically. So go from zero loads to whatever, fully loaded configuration of the structure we're looking at. Oftentimes, that's not the preferred approach to solving those types of problems. Instead, typically in a lot of these analyses, and especially as you move towards nonlinear analysis, the idea of assigning loads to the structure really requires that you not just apply the loads all at once, but instead try to ramp up the loading that you're applying to the structure. So maybe you increase the load a little bit, and then you actually solve for what's the kind of equilibrium state of the structure under this small kind of incremental increase in the load that you've applied to the structure. And then you increment that load again. So increase the load a little bit more, again, solve for equilibrium to try to kind of get this converged state of what the displaced state of the structure looks like. And then you continue in this fashion until you've reached the fully loaded configuration that you desire. But the nice thing about doing this incremental kind of loading approach to running a finite element problem in this sort of discretized sense of, take the load, break it up into these load steps, and then apply them in kind of this incremental fashion. The other advantage to doing this is that it actually enables you to do some interesting things. You don't just have to load up the structure monotonically, just like ramping up that load linearly. You could also subject the structure to cycles of loading. So take the load, increase it, maybe then decrease it, and then maybe kind of like reverse the direction of the loads. And that can happen in a lot of different practical scenarios where you might be interested in how does the structure behave under these kinds of cyclic loading deformations, as might occur during, let's say, an earthquake or something like that, where the structure isn't necessarily subjected to one instantaneous load. It's subjected to perhaps several cycles of loading, which can influence the overall behavior. And why do we want to do this? Why do we even care about cyclic behavior? Well, in general, if we were thinking of the structure as behaving in a strictly linear elastic sense, then it doesn't really matter whether we subject it to cyclic loads or whether we just consider what's the maximum load that the structure would be subjected to under those various cycles. Really, we only need to worry about cyclic loading if the behavior of the material is sensitive to the whole history of deformation that it has been subjected to. So that's certainly true for certain types of materials, especially elastoplastic materials, where if you were to take, let's say, some, I don't know, uniaxial bar, which I've idealized as this kind of one-dimensional spring, and we subject it to maybe a few cycles of loading, you can kind of see that the relationship between the strain in the material and the resulting stress in the material might exhibit this kind of, I don't know, nonlinear envelope. So initially, the material will behave elastically up to some critical point where at a certain point now it kind of flattens out and the stress strain slope becomes a little bit more shallow. We continue to load it out to some critical value, and then we reverse the direction of loading. And we see that when we reverse the direction of loading, or when we unload the material, we actually unload, in the case of this elastoplastic material, along a slope that's proportional to the original elastic modulus of the material. And you can imagine if we kind of do this multiple times and we notice some interesting behaviors might arise from doing this kind of cyclic or hysteretic kind of loading program, we might find that the material might exceed some kind of critical limit on, how much permanent deformation can it actually sustain before it ultimately ruptures or fractures or does something interesting like that. So ultimately, when we're considering any kind of nonlinear material behavior, we do really want to assign not just what's the total load that we're putting on the structure, but really what's the full history of loading so that we can better understand what's happening at the material level through some kind of full history of loading. That's really the key distinction here that I want to point out, which is kind of common to a lot of nonlinear material models and behaviors, is that they do depend not just on what's the current state of strain in the material. They often depend on the entire history of strain or history of loading that the material has experienced. So that's a critical distinction. But ultimately, what it means is that anytime we're running these types of analyses, we're not just saying, here's the current deformed state of the structure, or in other words, here's the current state of the displacements at all the nodes in the structure, use that information to figure out what's the current state of stress. Really, we want to approach this problem by saying, given some current, increment in the applied external loads we put on the structure, what is then the resulting increment in the displacements at each one of the nodes, which I'll call delta U. Delta U being kind of like the change in the displacement at any given node between any two of these kind of corresponding load steps. Or if you like, you can kind of discretize this kind of, variation in the loads as a function of time, and then define these kind of load steps as occurring at discrete times. Now, time doesn't necessarily need to mean actual wall time or time that you would read off of your watch. It could just be a pseudo time that doesn't necessarily have any dimensions to it. You're just using it to basically say, as I run my analysis, I want to kind of ramp up the load. But if you're assuming quasi-static conditions, then really, it doesn't really matter how quickly you apply the loads. So there are certain cases where that's not true, but we'll get into that momentarily. In any case, we suppose that over a given, step in this analysis, going from, let's say, time tn-1 to tn, we increase the load by a small amount. That results in some increase in the displacements, or delta U. And from these kind of increments in the displacement in each of the nodes, we can also then determine what's then the resulting increment in the strain that occurs within the material at some kind of integration point within one of the elements of this kind of finite element mesh or something like that. So the nice thing about taking this approach, and more specifically, the nice thing about the finite element method more generally, in the way that we've constructed it, in the way that we've partitioned out, different, collections of data and different procedures that we've kind of defined up to this point. The nice thing about this organization is that we've actually sort of separated out, this, notion of what's happening in the material from some of the other, steps we have to go through to actually formulate our finite element. So if you want, you can think of it kind of like this. At the nodes, we have things like, the displacements, or more specifically, if we're doing loading in this kind of incremental fashion, over a given load step, what we're looking at is rather the increment in the displacements of the nodes for the current load step. And given that increment in displacement, we can then formulate what's the corresponding increment in strain for the current load step. We can use our standard kind of strain displacement operator to figure out how these increments in displacement relate to corresponding increments in strain. And we can then determine what's the increment in strain at each one of the integration points inside of one of these elements. So at this point, we've kind of taken some quantities at the nodes, used our finite element formulation to construct our strain displacement operators, and then we spit out some values of these strain increments at different interior material points or integration points within the element. And at this stage, now we have to decide how are we going to determine the new state of stress in the material given the current increment in strain. And abstractly, you can kind of think of this operation of taking some, driven increment of strain and then coming up with some new stress in the material as involving some functional relationship between those two things. So given the strain increment, we want to find out what's the new stress in the material. And in a general sense, you can think of this functional relationship as precisely corresponding to what I'll call a material model. It is exactly this idea, a function that takes in the strain increment and passes back the new state of stress in the material at a given integration point. Then once you have that, well, you can come and use that new stress in the material to integrate what are the resulting forces that act at each one of the nodes of a given element. You can assemble those forces into whatever global system of equations you're trying to solve. You can use that to iterate and solve for equilibrium, assuming that this relationship might involve some nonlinear relationship between the strain increment and the corresponding stress in the material. But at the end of the day, our finite element formulation remains the same. If we're interested in generalizing this relationship to accommodate nonlinear material behavior, the only thing we have to change in this diagram is the material model. Everything else we can leave as exactly what we've discussed up to this point in the class. So our finite element formulations that involve, computing these strain displacement operators, using numerical integration to kind of integrate things over the elements to compute those, nodal forces, all that is consistent with what we've discussed. It's really just this part that we have to touch if we want to include nonlinear material behavior. So how exactly do we do that? How do we include this more general relationship and substitute in different options for different material models to represent new and interesting material behaviors? Well, like I said, it basically corresponds to defining some function, if you like. You could go to your finite element program, you can write it in MATLAB. There are even some commercial finite element software tools, like I think even ANSYS has some functionality to do this. Abacus, I think, has a fairly well-known functionality to implement your own user-defined material types, which basically are just, some kind of way for you to write your own material model in the format of some small program that you hand off to the finite element code. And then it takes your function, your user-defined material model, takes it in, and then it actually uses it to update what's the new stress in the material given the current strain increment. So if you want, you could go around and play with that, write your own user material subroutine. And all you need to do is implement exactly this relationship. Given some new strain increment, determine what's the new stress in the material at a given integration point. So very modular. You can kind of substitute in any kind of interesting relationship you like. Certainly, there are simple ones like basic elasticity and other things like that, but you can certainly program in a great deal of complexity into these models. So really, that's all a material model is. It's just this function, this feed-forward relationship that takes a strain increment, gives me back the current stress in the material. Now, besides that, I might also want something else. Not just what's the updated stress in the material given the current increment or applied increment in strain for the current load step. If I'm trying to assemble a system of equations and maybe use some kind of Newton-Raphson iteration procedure to achieve, convergence in my nonlinear solution algorithm, I might also need to compute what's the stiffness matrix, right? And the stiffness matrix, as we had defined previously, involves computing exactly this thing, the integral over the element of B transpose D times B, where D, as we had previously defined, was kind of that kind of assumed linear relationship between stress and strain. It was that kind of 6x6 matrix filled with all those different material coefficients. Now, in the more general case where we have this abstract material model, we can still assemble a stiffness matrix for the element, but we have to substitute in some more complicated expression for this matrix D. It is still a nice 6x6 matrix filled with a bunch of different entries, but the distinction here is that to determine what those entries of that matrix are, we have to basically take whatever this functional relationship for the stress dependent on the strain increment is, and then take the derivative of that function with respect to the inputs, or in other words, the strain increment. So you can think of it as basically the tangent stiffness of the material. It's sometimes called the tangent modulus operator, but basically it is nothing more than the derivative of the strain components with respect to the incoming strain components. Okay, that's all you really need to do. And what are some specific examples of material models that we might look at? Well, I'll use as a prototypical example an elastoplastic material model. I like this one because it includes a few specific concepts that I want to define here, which are that this function, which you might implement in a computer, might actually have a few additional pieces of data attached to it. And I'll refer to those two different collections of data in the following kind of way. The first collection of data that you might associate with a material model are what I'll call material parameters. These are things that you're probably familiar with in the case of linear elasticity. Material parameters for a linear elastic model really just refer to things like the Young's modulus and the Poisson's ratio. They characterize effectively the stiffness properties of the material. And they are assumed to be these material constants. And especially if we're assuming that the material behavior is homogeneous, that is to say that it's the same at all the different points in the structure, then we can kind of assume that those material parameters are things that are the same at basically every integration point in every element in the mesh. So they're parameters that we have to define. We have to go and do some measurements or physical experiments to actually characterize those parameters. And then we can hand them off and kind of put them into these models. But the model itself is, not just that functional relationship, but in general, it is a parameterized relationship. It's parameterized in terms of these specific constants or properties that we would have to define. And obviously, they can't just come out of nowhere. They have to be well validated against experimental data. Now, the other kind of collection of data that I have to associate with a material model is something that I'll call history variables or material state variables. These are kind of like internal additional variables, kind of like you would have as, the nodal displacements as being kind of like the primary variables that you're solving for in a finite element context. In addition to those, we also have some local variables stored by the material that the material model keeps track of over the full history of loading that we subject this kind of integration point to. So as we continue to update the stress in the material, as we kind of go over different load steps, we might find that these internal variables held by this material model will be updated, or they'll be changed to reflect how the internal state of the material has changed due to whatever loading we've subjected the material to. Good examples of these types of history variables are things like plastic strain, the amount of permanent deformation that might have occurred within the material, which is something that we certainly need to keep track of in order to, be able to say, well, how much permanent deformation has this material experienced, and how does that influence how this material should look after we've kind of like subjected it to this next load increment and things like that. So we have to keep track of these things in order to introduce history dependence into these kind of material models. There's no other way that you can include that history dependence. So in any case, we've defined our material model as consisting of a functional relationship to update stress given strain increments. It has to be parameterized in terms of these different coefficients or properties, and we have to also associate it with, some kind of history-dependent internal variables that get updated every time we call this function, or every time we kind of try to compute the new state of stress in the material. Okay, So obviously, we'll start with some of the simplest examples of material models that you're already familiar with, just as a baseline to kind of frame your, viewpoint and your state of reference. Isotropic elasticity. This is effectively what we've been talking about up to now, almost exclusively. We've referred to material behavior in this way, which says that there is this assumed linear relationship between all the different components of stress in the material and the resulting, the strain components in the material. So we were able to parameterize this relationship in terms of two material parameters, or two material properties corresponding to the elastic coefficients. You could parameterize that in terms of, Young's modulus and Poisson's ratio, or you could do it in terms of shear modulus and the Lemay parameter. Now, it's fairly straightforward to see that if we wanted to determine what's the tangent modulus of this particular material model, then it turns out that regardless of, how we've chosen to define our incoming strain increment, the resulting tangent modulus is the same. Or in other words, it's basically exactly this 6x6 matrix. So if we needed to use that to assemble our stiffness matrix for the element, that's the exact kind of expression that we would use. All right. And it's also worth mentioning that for linear elasticity, there are no history variables for this particular model, because it's assumed that the material doesn't behave any differently regardless of, how you've subjected it to various cycles of loading or the particular load path or strain incrementation that you've subjected it to. None of that really influences this fundamental relationship between strain and stress. So that's an important distinction. There's no path dependence in terms of how you've chosen to load the material, and really there's no need to keep track of any internal variables. Yeah.
So nonlinearity in materials wouldn't change the modulus. If it changes the modulus, that means this matrices would change.
Right. So there are ways that you can augment the stiffness, and I'll talk about that momentarily through maybe some kind of internal damage mechanism. So let's say that if the material stiffness were to degrade because you subjected it to relatively large strains and then it kind of loses some of its elastic stiffness, I would call that kind of a damage mechanism. But you do need to keep track of how much damage the material has experienced over some history of loading. And you can introduce that dependence on damage by actually introducing some damage parameter. It's basically a type of history variable that keeps track of how much the stiffness has been degraded. So I'll give an example of that a little bit later. But you're right, if you wanted to include some kind of degrading effects on the stiffness, you would need to introduce some history variable to take that into account. But if you assume that the material only remains elastic, it doesn't degrade at all, then you would be perfectly content to just accept that, there's no history dependence and it's just purely elastic behavior. Now, that's not to say that this is totally physical. Obviously, if you took this material outside of its reasonable bounds that it should operate in, if you know that like the material in the real world should fracture if you took it to really large values of stress or strain, then clearly this model is no longer valid. So anytime that you're using a material model that invokes certain assumptions or limiting behaviors, you do have to exercise caution and judgment, because ultimately it's up to you to decide, are these models really operating within their intended ranges of behaviors? And if they're not, that's something that you kind of have to assess. You can go back and check, well, in my analysis, did the stress ever exceed some kind of theoretical or kind of like experimental threshold? That's something that you have to verify. So just bear that in mind. All right. Other types of behaviors which are nonetheless elastic are something that I'll kind of broadly refer to as orthotropic elasticity. This is still elastic behavior, but elastic behavior which looks different depending on the orientation of the loading that I'm prescribing to some chunk of material. And a good example of an orthotropic elastic material is wood. It basically exhibits different material behaviors depending on whether you're loading this kind of block of wood, in a direction that's parallel to the grains of the wood or in a direction that's maybe transverse to those directions. So in general, if you're working with an orthotropic elastic material, you do have to specify not just, those kind of elastic properties of the material, but also what are the orientations of these different preferred directions of the material. perhaps, one of these preferred directions is aligned parallel to the grain of the wood, and maybe the other two directions are acting in some kind of transverse directions, perpendicular to that kind of axial direction. But if, let's say, I don't know, your structure has some member in it, which is inclined or oriented at some angle or something like that, you would need to actually account for what is the orientation of the material and reflect that in how you construct the material relationships between stress and strain. Because in general, it will depend on how you oriented the material. If you kind of like oriented the material, aligned with the X, Y, and Z axes, such that the preferred axes are aligned with those different kind of global axes, then you don't have to do any kind of transformation between what's the local state of stress in the material and strain in the material, relative to these kind of preferred or orthotropic material axes. But if the material is somehow oriented in a way that differs from those global axes, now you have to figure out a way of transforming the state of stress and strain in the material into a coordinate frame that's aligned with these preferred axes. And to do that transformation, you can arrange these different vectors, basically defined as unit vectors, into this format of a matrix, which, as it happens, it can be shown that this matrix corresponds to a three-dimensional rotation matrix. And if you can do this, if you can format this kind of nice rotation matrix Q to transform different vectors oriented in this global coordinate frame into the corresponding local coordinate frames of the material, then you can actually do some interesting transformations to not just transform vectors, but actually transform the stress and strain tensors into this kind of local coordinate frame specific to the material's local axes. So that's a little bit of a complication when we deal with these orthotropic types of materials. But at the end of the day, if we can do this transformation and relate not just the global and, like stress and strain tensors oriented in the global coordinate system, if we can transform them into this local coordinate system, which I'll denote with kind of like hatted symbols, then we can come up with a relationship between these kind of locally transformed stress and strain components that looks something like this. It's a little bit more complicated, and it involves dependence on a few additional parameters beyond what we're previously familiar with. So rather than just kind of Young's modulus and Poisson's ratio as being the only parameters we have to, come up with to characterize this behavior, now we have to come up with a total of 9 independent coefficients. And you can come up with these coefficients by just running a series of experiments that take some block of material and then, in different directions, maybe you load it uniaxially in the X direction, load it uniaxially in the Y direction, and in the Z direction, and you can come up with different values for the effective Young's modulus that would act in each of those 3 different mutually orthogonal directions, which I'll call EX, EY, EZ. And you can also measure under these different modes of uniaxial extension, what's the resulting apparent contraction or kind of, contraction strain in each of the lateral directions under a given kind of axial loading direction. And that's how you come up with these different values of the Poisson's ratio measured relative to a given loading direction. So you come up with all these different parameters. You also need the shear moduli in these different modes of shearing that differs depending on the orientation that you're shearing it in. So you might have like an XY shear, you might have a YZ shear, and maybe there's a ZX shear and all those different modes. So if you can do all those different tests, a total of 9 different tests, then you can come up with these different parameters. There may well be better ways to come up with these different coefficients, but in general, it's a little bit more work you have to do to come up with these values. All right. So that's orthotropic elasticity, a little bit more complicated, but nonetheless elastic and with no dependence on any kind of history or variables of interest. So we still assume that for orthotropic materials, there's no inelastic behavior. So we can kind of still apply the same concepts, determine the stiffness matrix or kind of like the tangent modulus of the material as just the inverse of this matrix shown. You'll notice I've defined this relationship kind of as the inverse of given stress, determine what's the strain, but you could just as well take this matrix, invert it, and now you have the tangent modulus of the material. Okay, so that's orthotropic elasticity, but enough with elastic behavior, right? We were really interested in nonlinear behavior. And more specifically, there are a few types of nonlinear material behavior that I might point to as specific examples of, behaviors of engineering materials that we care about. One good example is plasticity, where we load the material within some kind of reasonable range of stresses, and then when we reach some critical threshold, now the material appears to, lose some of its stiffness. As we continue to load it, it seems like it's just kind of lost most of its stiffness. Maybe it still retains a little bit of stiffness. And in this kind of range where the material is kind of like actively, yielding, as it's sometimes called, you'll still see maybe some residual increase in stress under different increases in strain. And that kind of range of still increasing stress is sometimes called strain hardening behavior. Now, eventually, if we unload the material, we'll unload along some kind of elastic slope. So that's really what's characteristic of plastic behavior, elastoplastic deformations. And it's usually associated with things like metals. Think steel or other types of materials, aluminum, copper, things like that. Most metals exhibit this kind of elastoplastic behavior that experience effectively a form of permanent deformation. It's kind of like what would happen if you took some bar, you stretched it, and then you removed the load, and it stayed, permanently stretched after you took the load off. That's effectively what this behavior represents. Another type of behavior that's kind of nonlinear is what I'll call, nonlinear elasticity, and even a little bit more than that, viscoelastic material behavior. This is behavior that incorporates some rate dependence into the applied loading that you put onto the material. And this can happen for a few different types of materials. It can happen for some types of soils, foams, elastomers, other types of polymers, and other types of materials like that. But this kind of rate dependence shows up when you try to load the material at increasing strain rates. So the faster you load the material, the higher the apparent internal state of stress in the material. And if you unload the material, then it looks like maybe you can unload it back all the way down to a state of zero stress, and you'll recover all of the strain that you put into the material. So you get back to this original starting point of, zero stress, zero strain. But along the way, maybe, this path of loading and unloading interior to this kind of region between those two curves, it will look like you've dissipated some energy. So viscoelastic materials in general do kind of dissipate energy through different cycles of loading. And that can sometimes be advantageous if you want to dissipate energy that would otherwise accumulate due to kind of like high frequency vibrations and things like that. But in general, this is kind of the phenomenon that you would see. And it need not necessarily be a perfectly straight line that represents that behavior. And in fact, many elastomers do exhibit this kind of behavior where they have some initial stiffness and then it kind of flattens out for a while and then it kind of like ticks up again in terms of its apparent stiffness. Other types of materials that are interesting include cohesive damage. This is where you might have a material, this is true of a lot of different composite materials and things like that, where you might load it up in tension up to a certain point. It'll maintain perfectly elastic behavior, but then at certain critical values of stress, much like in the case of plasticity, you'll notice that, you'll start to lose stiffness. And rather than having strain hardening behavior, where still you have increasing stress with respect to increasing strain, for these kinds of damaging materials with cohesive damage, you might see that instead you'll have strain softening, where the slope of this kind of stress strain curve now becomes negative. So it's kind of like you're losing stiffness. And in fact, that's how a lot of these cohesive damage models are represented. They're not necessarily represented as permanent deformation of the material, but rather a permanent degradation of the stiffness of those materials. So you might find that in general, if you were to unload this damaged piece of material, you could remove the load and it'll kind of go back to a state of zero strain and zero stress. But you'll notice that the stiffness of the material is kind of like reduced. And over time, as you continue to kind of like load it up further and kind of take it out even more, you'll increase the amount of damage or degradation in the material and kind of further degrade the apparent stiffness of the material. So a very different mechanism than plasticity, which assumes that when you unload the material, you maintain the original elastic stiffness of the material. Damage and kind of like cohesive failure of materials that kind of appears like this, instead, you permanently lose that stiffness. So it might look, if you're loading some kind of piece of material monotonically, it might not be apparent to you whether or not you're experiencing some kind of plastic, deformation, permanent deformation, or whether you're experiencing some kind of like loss of stiffness and damage. And the only way to know that is to kind of actually run a full cyclic loading cycle. So that's something to bear in mind if you're trying to take some kind of stress strain data to calibrate a constitutive model. You really do need to know what exactly is the behavior when I unload the material. That's important for characterizing these different effects. And then finally, oh yeah, go ahead.
Is this kind of like fatigue in material? Like every time in cyclic load, when you put load, its stiffness becomes lower, and so the material is in a fatigue cyclic.
I guess I would be a little cautious in distinguishing fatigue as being kind of a mechanism more associated with like fracture propagation at kind of like a very small micro scale in the material. But in general, it is possible that you can accumulate damage through kind of like relatively low or even high cycle loading of the material. So over time, you'll induce kind of like small scale damage in the material that could actually result in degradations of stiffness. There are certain cases where maybe you're like doing some kind of hysteretic loading loop of some material, and it might initially look like it's, being deformed plastically, and then, it's almost like this first curve on the top half here. But then over multiple cycles of loading, maybe these kind of hysteresis loops kind of start collapsing. And in effect, what you're observing is kind of two different phenomena almost happening, in combination, both some amount of plasticity and some damage. So kind of like as this dimension shrinks further and as the apparent stiffness of the, stress strain curve as you elastically unload it, if that's decreasing, then I would call that damage. But in general, yeah, you kind of have to distinguish how much of this is plasticity, how much of it is damage. And those two things can be combined and, integrated into one model that is, sometimes called a damage plasticity model. Very complicated models, but you can't have both of those things happening at the same time. So in general, you kind of have to figure out what's the best parameterization to approximate these things. But yeah, good question. The last one I'll point to is just simple brittle fracture. It's where you load the material up to some critical threshold of stress or strain, and it just fails. It just kind of breaks apart. And that's typical of things like glass or other types of classically brittle materials. Sometimes you could even, idealize concrete under tension as being kind of a brittle type, characteristically brittle material. It doesn't exhibit any kind of softening behavior. It just fails. It doesn't even kind of like lose stiffness. It's just like that pretty much. So slightly different behaviors. And the things that I want to point out here is that a lot of different behaviors can also be worked in besides these kind of ones that I've shown here. In the case of elasticity, there's a whole slew of different things that we could work in. We've talked about isotropic versus orthotropic material behaviors. So orientation dependent, stiffness of the material, linear versus nonlinear elasticity. So instead of having a directly, linear or kind of straight line relationship between stress and strain, maybe it kind of has some kind of nonlinear curved relationship. As you get into the subject of large deformations, if you subject some chunk of material to really, really large strains, sometimes the material will exhibit very different behaviors at large strains as compared to what it would exhibit at relatively small strains. So there are various formulations that look at how to deal with that, either in an incremental or a hyperelastic context. We might get into that later. There's certainly, strain rate dependence, generally called viscoelasticity, what we've already talked about. And then there's also temperature dependence, things like thermal expansion, but also potentially, reductions in the apparent stiffness of the material as you increase the internal temperature of the material. So there's a lot of interesting things, even with just elastic behavior, that you can kind of factor in here that represent and try to approximate different behaviors. And then on the side of plasticity, let's say, and maybe some of the other kind of cohesive damage modeling frameworks, we can include similar effects. We can include also isotropy or anisotropy with respect to, the actual plastic deformations that might occur in the material. We can build in strain rate dependence in terms of how we load the material plastically. That's sometimes called viscoplasticity. We can include pressure dependence. So depending on how much confinement or how much pressure the material is subjected to, maybe it yields at in some earlier time if it's subjected to less pressure, or maybe, you know, it exhibits some kind of interesting pressure dependent behavior that's more typical of granular materials, soils, things like that. You can also have various types of hardening behavior, how exactly the material regains or kind of like increases in apparent stiffness as you continue to load it under these kind of like plastically deforming scenarios. That kind of introduces a lot of interesting things, and certainly also temperature dependence. So there's a huge number of different factors that you can include in your model to try to accommodate these different phenomena. And it really gets overwhelming very quickly, because you can kind of imagine, you know, how complicated some of these models can become just by saying, well, I want to represent some kind of damage and plasticity, and maybe there's some interesting curvature I want to build into how these kind of stress strain diagrams get constructed. But the things that I want to, you know, assert, at least before you kind of go off and try to start calibrating material models, is that really your models are only as good as the data that you use to try to calibrate them. So in general, if you're trying to come up with some calibrated representation of some interesting behavior, like this concrete cylinder being subjected to perhaps multiple cycles of loading and pushing it to kind of like increasing values of compression, you can kind of see maybe it exhibits behavior that looks kind of like plasticity up to a point, and then it kind of damages past a certain point, and then maybe it has some residual stress. Now, as you try to accommodate these different behaviors, you have to include more and more parameters for the model. And as you increase the number of parameters in these models, you also increase the modeling uncertainty associated with those parameters. And this is really the crucial point, is that anytime you increase the complexity of these models and include more parameters, you really do have to increase the amount of experiments that you're running to try to validate these models and calibrate those parameters to make sure that they're representative of the actual material behavior you're trying to match. And so you should always try to determine, well, what kind of material behavior am I trying to represent? Is it maybe some kind of concrete under compressive loading? Is it some kind of steel material under kind of like hysteretic loading? And depending on the loading regime and other kinds of scenarios like that, at what temperature is this material being loaded? And all these different kind of environmental factors have to be taken into consideration. You do need to spend some time and think about, well, is this the right model for the job? And do I have sufficient data to kind of corroborate like my experiments, or even kind of like to justify my choice of these different parameters? So that's really one of the biggest sources of modeling uncertainty, is how you actually choose to define these parameters and how you choose to pick these different models and the types of effects that they can include. It'd be really cool to have one model to rule them all, right? There's one model that's the perfect model that you should always use to try to represent concrete or, you know, plasticity in steel or something like that. But there isn't such a thing. I mean, you know, people have worked very hard to try to improve upon the models over the decades, but, you know, it's a never-ending game of trying to come up with the better model, the better data and the parameterization to fit it. It's just something that you should be cautious of whenever you're trying to come up with some kind of numerical model to represent these nonlinear behaviors. So with that, I'll kind of end it here and just say, especially as you consider getting started on your project, do think about how this pertains to you. Certainly, ANSYS has a number of built-in material models, and not just material models that lack a parameterization, but rather they are a material model equipped with a pre-parameterization, or in other words, they already have some material coefficients or material properties assigned for certain common engineering materials you might encounter, including common structural materials, steel, concrete, etc., all those fun things that you might be tempted to use. But I will caution you, be very careful whenever you're using a model that you have not yourself validated and kind of gone through the process of verifying that it, you know, represents the types of behaviors that you need for the analysis that you're running. If you, let's say, take some model that exhibits no temperature dependence, and then you say, oh, I want to model a building under kind of these like extreme, you know, high temperature conditions, then it's really not going to be well suited to represent those behaviors. Similarly, it's just as bad if you were to try to run a purely linear elastic model when you know that the material should be failing or doing some other kind of interesting behavior. So in general, I would say if you are trying to just stick within this linear elastic regime, or even within a reasonable kind of nonlinear elastoplastic regime, these types of models, these pre-calibrated models, are probably okay to use. And they're certainly a great starting point if you just want to get something working and you want to test out your, finite element analysis and just have something to, baseline your analysis against. But in general, if you are trying to really emphasize the use of nonlinear material behavior, if that's core to the, the problem that you're trying to address, then you should really be the one to determine what's the appropriate model to use, how has it been validated, do I need to do some additional validation against experimental data that I've collected in order to parameterize my own model and do things like that? So do give some time to that and do give some thought to that, because I think that's going to be really critical, not just for your project, but in general, as you kind of go out in practice and try to use these tools. Okay, so that's all we have time for today, but we'll pick up on Wednesday, continuing this same subject. Any questions before we end it? Okay, I'll see you then. Yeah. Yeah. Mm-hmm.